Physics uses time everywhere. Every equation, every prediction, every experiment. From the motion of planets to the decay of particles, from the evolution of stars to the behavior of atoms, time is present in every calculation physics makes. It is the variable against which change is measured, the parameter that allows events to be ordered, and the reference that gives meaning to words like before, after, and simultaneous. And yet physics has never explained what time physically is. Not what it measures, not how it flows, not why it exists, only that it is there. In physics, time appears as a parameter, a symbol written into equations that allows one state of a system to be related to another. When physicists write down the laws of motion, they describe how positions, velocities, or fields change with respect to time. The equations work with extraordinary accuracy. They predict outcomes to many decimal places. They allow spacecraft to be navigated across the solar system and particles to be guided inside accelerators with astonishing precision. But nowhere in those equations is time itself defined. It is assumed. Physics does not describe time acting on the world. It does not specify a mechanism by which time causes events to unfold. Instead, it describes the world changing relative to time. Time is the background coordinate against which motion is expressed, not an actor within the theory. Time is not treated as something that happens. It is treated as something everything happens within. This assumption is so deeply embedded that it often goes unnoticed. The success of the equations makes the absence of a definition easy to ignore. But when examined closely, the omission is striking. Physics relies on time at every step, yet never includes it as a physical entity with properties, structure, or dynamics of its own. In classical mechanics, time is absolute. It flows uniformly, the same everywhere, for all observers, regardless of what is happening in the universe. Newton described time as something that flows equably, without relation to anything external. In this view, time exists independently of matter, motion, or observation. Events occur within time, but time itself is unaffected by them. This absolute time provided a stable foundation for classical physics. It allowed motion to be described unambiguously, and causality to be ordered cleanly. But even here, time was never explained. Newton did not describe what this flow physically consisted of, how it originated, or why it should exist at all. Time was not measured by the theory. It was presumed by it. There was no mechanism behind the flow, no physical process identified as time itself, no interaction between time and matter. It simply ticked in the background of reality, silently and universally. Einstein's theories of relativity transformed this picture. Absolute time was abandoned. Time became relative, intertwined with space and dependent on the motion of observers. Two clocks moving differently or experiencing different gravitational fields would not agree on the passage of time. Time could stretch, slow down, or contract depending on the circumstances. This was a radical shift. Time was no longer universal. It became local. It became something that behaved differently depending on physical conditions. But relativity did not define what time is. It redefined how time behaves, not what exists. Redefined is the operative word. In Einstein's framework, time becomes part of space-time, a four-dimensional geometric structure that combines spatial dimensions with temporal ones. Events are located within this structure, and the geometry determines how clocks tick and how paths through space-time unfold. Space-time sets the rules for measurement. Yet geometry is still description, not substance. Space-time tells us how distances and durations relate, how trajectories curve, and how measurements compare between observers. It does not tell us what time itself physically consists of, or why this geometric dimension should exist, rather than some other structure. Relativity tells us how time changes. It does not tell us what changes. At the smallest scales of nature, the situation becomes even more peculiar. In quantum mechanics, time is not treated in the same way as other physical quantities. Position is represented by an operator. Momentum is represented by an operator. Energy is represented by an operator. These quantities are measurable, subject to uncertainty relations, and intrinsic to the systems being described. Time is not. In quantum mechanics, time enters the equations as an external parameter. It is not something the system possesses. It is something the system evolves with respect to. The famous Schrödinger equation describes how a quantum state changes over time, but time itself remains outside the quantum description. There is no quantum operator corresponding to time. There is no uncertainty principle involving time in the same way as position and momentum. There is no quantum observable that represents time as part of the system. The theory that governs the most fundamental constituents of reality cannot place time inside its own framework. This creates a strange hierarchy. Quantum systems are described as evolving in time, but time itself is treated as classical, fixed, and external. The deepest theory of matter relies on a concept it cannot internalize. Across physics, time appears in incompatible roles. Classical mechanics assumes absolute time. Relativity describes relative, geometric time. Quantum mechanics uses external, classical time. Each framework works extraordinarily well within its domain. Each has been confirmed by countless experiments. Each relies critically on time. None explain what time physically is. There is no single definition of time shared across theories. There is no unified account of its nature that survives when moving from one framework to another. Time changes its role depending on the theory, but its existence is never justified or explained. This inconsistency is not a flaw in any single theory. It is a structural feature of physics as a whole. Despite this, physics measures time with extraordinary precision. Atomic clocks, based on quantum transitions, lose less than a second over the age of the universe. Timekeeping has become so accurate that tiny effects predicted by relativity must be corrected for in everyday technologies like GPS. But clocks do not measure time itself. They measure processes. They measure oscillations of atoms, vibrations of crystals, or transitions between energy levels. What we call time is inferred by counting these changes. We observe one process repeating and use it as a reference to label the change of others. We do not observe time passing. We observe systems changing and assign a temporal label to that change. The distinction is subtle but crucial. A clock does not reveal the substance of time. It reveals the regularity of a physical process. The assumption that time itself flows is not something measured directly. It is inferred from the consistency of change. Physics can predict these changes with astonishing accuracy. It can calculate how systems evolve, how long processes take, and how events are ordered. But the thing those changes are measured against remains unaccounted for. Time functions as an indispensable reference frame, not as a physical entity with its own description. This absence is not due to a lack of experimental data. It is not because the relevant measurements are too difficult to perform. It is not because technology has not advanced far enough. It is structural. Physics requires time in order to function, but cannot include time as a physical object within its own theories. It is present in every calculation and absent from every ontology. Time is everywhere in the equations and nowhere in the physical inventory of the world. Theories of physics describe what happens at moments in time, how systems change over durations, and how events relate temporally. But when asked what time itself is, the theories fall silent. This silence is not accidental. It reflects the way physics is constructed. Time is treated as a prerequisite for description, rather than something to be described. It is the stage on which physical processes unfold, not one of the actors on that stage. As a result, physics can model the behavior of matter and energy across vast ranges of scale, from subatomic particles to the evolution of the cosmos, while remaining unable to say what time itself physically is. This omission is not a paradox that produces contradictions in experiments. The equations work. The predictions hold. The technology functions. The success of physics is not undermined by this omission. But the omission remains. Physics can calculate how systems change with extraordinary precision. It can reconstruct the past and predict the future. It can synchronize clocks across continents and guide spacecraft across interplanetary space. Yet the thing that makes change intelligible in the first place remains undefined. Time is used, measured, relied upon. And despite all of this precision, physics cannot say what time itself physically is.